Hi there, Physics 152. You're the theorist for this week, week 9, in which you'll be looking at an interference pattern from a double slit or a single slit. So it looks kind of like this. This is what you'll see on the screen, a whole lot of little red dots. And the bright dots are called fringes, and then the space in between them are called dark fringes, I guess, bright fringes and dark fringes. And so you are going to be, I guess, counting fringes, measuring the distance, and basically finding the fringe distance. So let's go through some of the theory of how you find this fringe spacing. So this is from your book, actually. This is the wave optics chapter, section 33.2, the Young's double slit experiment. That's sort of the picture. So I'm just sort of going through night there this way. So then I'll start with double slit, and then we'll go to single slits. It's a little bit harder to understand, analyze single slit diffraction. But basically, let's start by drawing. There's a double slit. It'll be kind of small. There's laser light coming from the left there, some wavelength, a single wavelength light. And then, so that's a double slit. Over here is the viewing screen. And we'll set the viewing screen to be the y-axis. Right down the center, we'll call that y equals 0. And then a point up here is point P at an angle theta away from the screen. And the screen is a distance L from the slit. So that's sort of the view from above. Let's zoom in on this little part here. So you can sort of see the wall there. There's one slit, another slit. They're very narrow slits here, and they're separated by a distance d between the slits. And what you can imagine is that these two light, if they're going up to point P, there's sort of parallel beams, or almost parallel beams, both going at an angle theta. And so you can drop a right angle there, and that's an angle theta there. And this distance right there is the path difference to the point P on the screen. The bottom path has to go a little bit farther than the top path by just that delta r distance. There's a right triangle here where the hypotenuse is d, the slit separation, theta is that angle there, and then delta r is the path difference. Call that equation 1. And bright fringes are going to be when delta r equals m times theta, where m is some integer. And dark fringes will be when delta r are half integers, multiples of lambda, the wavelength. And so there you go. And then the other idea here is you can use the whole geometry to find y, that distance on the screen, with the distance to the screen. It's the same angle theta there. So sine theta equals y over L. That's, call that equation 2. Sine theta equals sine theta. You would say that the delta r over d is equal to y over L. And so that the bright fringes are going to be when y equals L times lambda over d times m, that integer. And that gives you adjacent fringes should be spaced by delta y is L lambda over d. Okay, so let's do single slit. That's a little harder as it turns out. That's the same basic setup. You've got laser light, some wavelength, monochromatic laser light coming from the left. It goes through the slit. There's a screen way over here on the right. There's a point P at some angle theta, and the distance between the slit and the screen is L. So, and it turns out that if, sort of by symmetry, at theta equals 0, laser light will constructively interfere. I'm just going to call this like bisymmetry. So there will be a bright central maximum. Now then, so you want to get where it gets dark on either side of the maximum. So the way you do this, again, we'll zoom in on this little part here. So there's the wall, there's kind of the distance. We call the slit width A here, traditionally. And same kind of thing, this light is all going to go off at a particular angle to point P, call that theta. But what we do is take this little, I've got a little compass here, and make half the distance, half a slit width a over 2. You can form the entire thing with pairs of points that are all a over 2 apart. And if you do that, and if you set delta r, the path difference, to be lambda over 2, they'll all destructively interfere. You'll get 0 from all these pairs, so you'll get a dark fringe. That's the argument that they make. So you make a lot of pairs. If they're all 0, then you should all get, and if you can fill the whole space, so you can solve that out again with the geometry, same as how we did with double slit. You get y dark is 2L over A times delta R. And if delta R is lambda over 2, then the 2's cancel, and you just get that the dark fringes are at L times lambda over A at a particular point. But let's draw this again, and what I'll convince you of, if I make going down to A over 4, a quarter of the slit width, then I can form pairs of A over 4 to cover the top half, and then again pairs of A over 4 to cover the bottom half. So what I'm saying here is you can also fill the same space twice with pairs of points that are A over 4 apart. And they will all, if you again set delta R to be lambda over 2, half a wavelength, and so it turns out to be 4L over A times delta R, then I think the 4 divided by 2 is 2. You get 2. Also, you can do it with A over 6. You just fill it up 3 times with pairs that are A over 6. That will give you dark fringes at 3L lambda over A. And you can sort of see where this is going. So there's dark fringes at y is equal to m, where m is an integer, L lambda over A, where m is plus or minus 1, plus or minus 2, but not 0. You skip the central bright fringe. But basically, the fringe spacing there for the dark fringes is L lambda over A. So I hope that helps your theory, and good luck with lab this week. Bye-bye.